If we ask for the fundamental difference between thermal light and laser light, we learned that coherence is one measure. However, we can make incoherent sources quite coherent by filtering spatially and frequency-wise, and still the light coming out of such a source will be very different in comparison to a laser source. And the main fundamental difference is the statistics in the photon emission. So, to understand what's happening, we have 4 points on the agenda. Number 1 is coherent thermal radiation. Number 2, Bose-Einstein statistic, that is for thermal radiation. Glauber states and Poisson statistics, that is for laser emission. And last not least, an experiment with which we very clearly can separate the 2 types of emissions and measure the statistics of photons emitted coherently in a laser source or statistically in a thermal source. As a motivation, we know if we have a thermal source with a lot of wavelengths, broadband emission, and a very random phase distribution in space, then we can select longitudinal coherence by a corresponding frequency filter, and we can select spatial coherence, increase spatial coherence by a small slit, in which we then only take very small parts of the phase fronts. However, in this we lose a lot of intensity, and yet still don't have coherent light. We have very low bandwidth light and highly spatial sorted light, but it's not laser light. If we look at the statistics for a thermal emitter, we can use an ansatz in using a Hamiltonian, which is actually a harmonic oscillator sorting the square of the electric field, that is the intensity, the photons. So we make a photon count, and if we look at the probability to find an n-photon state, which is given by this notation here, we use the Bose-Einstein statistics, which basically work with the thermal distribution. You recognize here the classical Boltzmann distribution, e to the minus h bar omega. N is the number of photons divided by kBt, kb the Boltzmann constant. The whole thing is normalized to a state sum. And if we look at the average number of photons in a specific state, this may remind you on Planck's formula, where we have exactly the statistics 1 over e to the h bar omega over kBt minus 1, which is the Bose-Einstein distribution. If you plot now the probability to measure n photons over the number of photons, then the highest probability is to measure no photon at all, and the probability distribution increases with small average number of photons. The more photons we measure, the more equal distributed is the curve, is the dependency. In the limit of very high photon numbers, this is more or less a straight line. So it says the probability to measure photons is pretty much the same, independent of the number of photons. On the other hand, if we look at coherent states, it can be shown that for a laser, that for stimulated emission of radiation, the states can be parameterized by a complex number alpha, and then the probability to measure n photons in a state is given by the projection of that complex parameter to one of the states, and this distribution shows an exponential behavior, which is called the Poisson distribution. Important here is that the width of the distribution is proportional to the root of the average number of photons we measure. So if we plot now the probability to measure n photons over the photon number, we will find the highest value, of course, at the average number of photons. So in this case for 20 it will be here, and it will be a symmetric distribution, totally different compared to the Bose-Einstein statistics we saw in the last picture. And an important characteristic of that distribution is that the width of the distribution scales with the root of the average number of photons we measure in a state. So that means that yes, this width increases with large numbers. Here, if you have only 5, the width is smaller. However, the relative width, if you define this by expectation value of n, then we get a delta n over n scales with 1 over the root of the average number. And that means that the relative width of the distribution gets smaller and smaller with higher number of photons. And that is very characteristic for laser photons. So the more we have in a mode, the sharper the measurement in terms of number of average photons will be. We can measure this difference in the so-called Hanbury Brown Twiss experiment. In this experiment we have a light source, a beam splitter, and then we, very similar to the Michelson interferometer, split up the beam into 2 beams and measure with 2 detectors at certain distances from the beam splitter. And then the critical situation will be when the distance of the 2 detectors to the beam splitter will be the same for both beam splitters, because then we will have a statistic in which we count, so to say, at the same time when a photon reaches this beam splitter, will it go through or will it go to the other direction? And as a consequence of the analysis, we can calculate a correlation function for the 2 beams and the photons coming through the beam splitter. This correlation function is listed here, and as a result we find, and I start with the plot of the result, if you plot here the time difference of the beam path of the 2 beams to detector 1 and detector 2, the interesting thing appears when we make this time smaller and smaller and approach the value of 0, when we really come to the point when we have no travel distance between the photons arriving at detector 1 or detector 2. And what we observe is that the correlation of the 2 beams is 2 for thermal radiation and it's 1 for laser radiation. It is independent of the time difference if we look at laser radiation. So the correlation of the laser photons at this point of no time difference of the beam passes is minimum. And that means that each individual photon, so to speak, can either be transmitted or it can be reflected at the beam splitter, and it will be a very consistent situation. So the photons will arrive more or less as a pearl of strings. They will come in very equidistant ways, so they will be very constant in intensity. In this case we have a measurement where we measure all the time an average of 4 photons, and as you remember from the Poisson distribution, this is very reproducible. It will be very likely to always measure this average number of photons, whereas in thermal light we will have a very statistical emission, and sometimes we'll have 1 photon, sometimes we'll have 2 or 5 or 8. To summarize, you see now here for a value of 20 photons, an average number of 20 photons, that using a thermal light source we will have a more or less already very similar to equal distribution of the probability, so it is quite likely to measure 5 or 35 photons. It's not a big difference if we repeat the measurement. However, if we repeat the measurement from laser photons, we will very likely always measure the average value, and that is the consequence of this extreme sorted and organized stimulated emission process leading to a very constant intensity emission of radiation.